Hello and welcome to this webinar entitled USB Type-C, a New Power Paradigm. In this presentation, we're going to explore what USB Type-C is, and more specifically, what USB power delivery is. We'll start with some historical background, then a little bit about what USB Type-C is, then we'll talk about what USB power delivery is, including the different modes. What is negotiation for power delivery? What are EMI cables? What is dual role for power? And what is programmable power supply? Then we'll get into some implementation details about the power source and the data line protection, and then wrap it up. The whole idea of a universal serial bus, USB, was to simplify connections made to personal computers. In the early 80s, when they first came out, they had a wide variety of connectors. You had everything from DIN connectors for the keyboard, DE9 connectors for the mouse, DB25 connectors for serial ports, and then using the opposite polarity DB25 for the printer port, matched to a Centronics connector at the printer. They were all large and they all required their own software drivers. In the early 90s, 7 computer companies got together to define a standard for a universal connector, with the idea being to replace all these other connectors with a single one that would also provide a little bit of power. In 1996, the first USB specification was released and the first ports appeared on Apple's iMac. This standard consisted of 2 connectors, a Type A connector and a Type B connector. The idea being that the consumer would not mix up which end to connect to what part. One of the unique features of the new cable was the ability to provide fast, at the time, data stream and power together. This allowed it to be used to power keyboards and mice. At this time, MP3 players and cell phones were starting to take off. They all came with their own small proprietary connectors. So 4 years later, in 2000, the Mini Port B connector was introduced to provide data and power to these devices. The miniaturization of phones continued while music players disappeared, and 5 years later, the Micro B connector was introduced to be able to plug into thinner devices. Also, the first battery charging specification came out. People were transferring more data with external drives and USB sticks, so the speed needed to increase. To do that, they had to add more contacts for more data lines, going from 4 pins to 8 pins. This required new connectors at each end, which were introduced in the late 2008 as USB 3.0. The Type A was backward compatible but the new large B end was too big to plug into many devices. So 2 years later, they introduced the micro USB 3 connector, and at the same time upped the transfer speed to 10 gigabits per second. In the meantime, things regressed. As the need for more bandwidth and capabilities increased, the standard lagged. Video and power needed more. Finally, in 2014, the USB Type-C was defined and introduced into the market. A specification for power was also introduced along the way. In late 2019, USB Power Delivery version 3 came out, which is the topic of this session. This is a historical timeline of when the different types of connectors were introduced, along with the increase in data speed. The part we're most interested in is in the center, where the power available through the connector was developed from 5 volts 100 milliamps through to 100 watts today. You can see at one time there was a battery charging specification called USB battery charging. USB Power Delivery version 1 came out in 2012, and the latest release was August 2019, coinciding with USB 4 SuperSpeed Plus. You can see the progression of increased power through time. A lot of thought has gone into the USB Type-C connector and cable. The intent is to replace as many cables as possible with this one type. First of all, the connector itself is thinner, slightly smaller than the Micro B connector, which was the smallest of the previous 7 types. It's reversible. It plugs in without regard to orientation. The same connector is at both ends of the cable, making the cable reversible as well, This is extremely convenient. I don't know about you, but for me, whenever I try to plug in a Type A connector, I get it wrong 150% of the time. I first try it without forcing it, and if it's not right, I flip it. But then it doesn't seem right again, so I flip it again, and then it might go in. The new connector itself is more robust, designed for 10,000 insertions, which is up from 5,000 for the mini USB and for only 1,500 on a standard USB-A connector. This allows you to plug and unplug the connector twice a day for the next 14 years. It's more rugged because the spring contacts, which are the wear parts, are now on the cable connector instead of the socket. Replacing a cable is easier than replacing a socket in your device. The cable has 5 data pair lines, which enables speeds of up to 40 gigabits per second under USB 4, so it has an incredible amount of speed and is still backward compatible with the lower speeds. It can deliver more power. It's the first connector to fully support USB power delivery, scaling anywhere up to 100 watts, and this power can be bidirectional. We'll be looking at that later. The cable can support multiple data protocols today, and with alternate mode can support future protocols. And it can handle all the existing video protocols, showing its extreme flexibility. The intent is for the cable to be reasonably future-proof. The new connector has 24 pins arranged in 2 rows of diagonally opposite symmetrical pins. 4 pins on the outside are for ground, and 4 pins are for V-bus in the middle. The original D+ and D- data pair are in the center, plus 2 additional data pairs on each side. This makes it easy to implement the original USB 3.0 with its 2 extra pairs, but leaves room to use all 4 for even more speed. Around the center D+, D- pair are 4 lines that make the system very versatile. The configuration channel, CC, and VCON are used to establish cable orientation and communication between devices for configuration. This is very important because it allows the devices to establish how they'll use the cable, and as we'll see, allows for dynamic use of the cable. The sub B1 and 2 channels are configurable for low-speed data lines for alternate mode, which makes it customizable. These can even be used for audio. This is what the Type-C receptacle looks like. You can see in the ratings that together the 4 power pins are rated for 5 amps, whereas all the other pins are rated for 1/4 amp at a working voltage of 20 volts. The maximum withstand voltage is 100. With a pitch spacing of only 0.5 millimeters, the interface needs to be able to handle possible shorts between pins during insertion and detachment. The big improvement is the very fast bidirectional data transfer and the ability to support a significant amount of bidirectional power that can be dynamically changed. The idea being, as shown in this example, where you might have a 2-monitor setup for a laptop. You have only one adapter into the wall that connects to the first monitor. A single cable runs to the other monitor, and from there down to your laptop. The laptop can now send video to the monitors, and the laptop battery can be charged from the monitors. You can also add your phone to the string. Instead of having a docking station, you can just plug in your USB cable to your monitor, and that will take care of all the interfaces that you need. This slide shows the progression of USB power, starting out with 5 volts, 100 milliamps per device, or in high power mode, 500 milliamps. Initially, the total power available was 2.5 watts. It was not until USB 3.0 came along that this was increased to 150 milliamps or 900 milliamps in high power mode. To address battery charging, USB-BC for battery charging came out, allowing for up to 1.5 amps at 5 volts. The first USB Type-C power spec allowed 5 volts at 1.5 amps as well. This was later increased to 3 amps, which is still only 15 watts. It wasn't until USB Power Delivery 3 and the USB Type-C connector, that voltage was increased to 20 volts with up to 5 amps, which is 100 watts. An important concept of the specification is that ports, that is, sources and sinks, are self-protecting. Sources are referred to as down-facing ports, DFP. They must be able to protect themselves from things like short circuits, overvoltage, overtemperature, and ESD. They must not rely on anything that's plugged into the port to protect it. It should be noted that there is no power on the pins until something is plugged in and the power is negotiated. We'll cover that in a few slides. The default voltage is 5 volts to be backwards compatible. The ports need to be able to discharge themselves when they're disconnected. The devices that use power are called sinks and referred to as up-facing ports, UFP. Once again, the sinks must be able to protect themselves from any input voltage that's too high or too low, or over temperature and over current, and they need to be able to discharge themselves when they're disconnected. Neither port depends on the other for any type of protection because they are self-protected. Sinks negotiate the power they'll receive before getting it. What is USB Power Delivery 3.0? It's a separate specification with more than 600 pages. It refers to a single wire protocol that's used on the configuration channel, CC, to communicate between two devices and basically unlocks the capabilities of those devices and the cable itself. There's a messaging protocol that occurs over this line, independent of all other data, and it's used for negotiation between the two devices that are connected together. Power roles, voltage and current levels, data roles, and even alternate mode are all defined. The down-facing port is the bus master, and it initiates all the communication messages, which are in a 32-bit biphase mark format, running at 300 kilobaud with error detection. You can see from this block diagram that things are getting a lot more complicated. Not all the devices that plug into a USB Type-C port will have a microcontroller that can negotiate power, so there's a mechanism to provide default power to legacy devices. This will always be 5 volts. There will also be lots of adapter cables that go from USB Type-C to the older Type A and Type B connectors to connect the legacy devices. For these and for newer ones, there's a mechanism to provide 5 volts at various current levels of 500 or 900 milliamps, 1.5 amps, or 3 amps. The source advertises its capabilities on the CC line by using a specific value of pull-up resistor that can be seen in this table. This resistor is in series with the sink's RD pull-down resistor, which creates a voltage divider. Based on the voltage present on the CC line, the sink can tell how much current is available. Devices that can't measure that voltage just get the default high power mode. The normal power delivery scheme begins when the cables are connected. The CC communication line is used to determine the connector orientation, and then the microprocessor applies 5 volts to the VCON line. This is important to see if the cable is E-marked, indicating additional capabilities. We'll get to that in a minute. Now that communication is established between the two devices, they negotiate. The source advertises its capabilities, and the sink selects one of those. The source sets up, and the V-bus is activated. Through the communications line, the two devices can talk to each other and request a change like a different voltage or current, or even swap roles at any time if they're capable. These are the basic power rules. More power is available through the cable because the voltages are increased. Standard cables are rated for 3 amps. The standard voltages are 5 volts, 9 volts, 15 volts, and 20 volts. Oddly, 12 volts is not included here, but it's actually often used as an example in the specification. Standard cables support 3 amps, allowing up to 60 watts of power. E-marked cables are capable of up to 5 amps with a heavier wiring. Any device that supports a higher voltage then the default 5 volts must also support the lower voltages. So if your device can supply 15 volts, it has to be able to supply 9 and 5 volts. Not all cables are the same. The default USB Type-C cable is only rated for USB 2.0 for data speed and a current carrying capability of 3 amps. You'll actually find there are a lot of long cables coming out, 10 to 15 feet in length, because they're going to be used for charging your laptop from a wall outlet. Power with no data. High-speed cables that support USB 3.2 Generation 2, which is 10 gigabits per second or higher for data, and or 5 amps of current must be electronically marked. This means there's an IC in one of the connectors that is connected to the CC line A5 for communication. Diagonally opposite is the VCON pin B5, which is terminated to ground with a 1K resistor, indicating that it needs 5 volts applied to power the IC. This is how the devices can detect the eMark cables, indicating its enhanced capabilities for data and power. These high-speed cables will be shorter and have a larger diameter and be more expensive. There are some new modes available with USB power delivery, and one of them is called dual role for power. This means that the devices and the corresponding port can be both a source and a sink. This makes sense for a laptop, for example. USB Type-C port could be connected to a charger, taking in power to refresh its battery, and then later connected to a cell phone, outputting power to charge it. Two devices with dual role for power capability can swap roles at any time. Laptop battery low, power it from your cell phone long enough to save your work. Understand that not every port will support this because it's a special feature. To advertise this feature, the port continually toggles the two CC pins high and low. This has no effect on the previous modes because the voltage is only checked during the high toggle. When similar capable devices are connected, they recognize the pattern. Programmable power supply is another feature that's defined in the specification, but may not be implemented in every port or device. It literally turns the USB Type-C port into a programmable power supply with fully adjustable constant voltage and or constant current. The voltage can be adjusted between 3.3 and 21 volts in fine increments like 20 millivolts. Similarly, the current can be adjusted as a limit or as a constant current source in small increments like 50 milliamps. If the sink is a battery charger, it can request a power profile that dynamically changes with the charge state of the battery without ever having any power circuitry itself. LED lighting would be another good example of something where you could control the dimming of the light with the power source. There are a couple of ways to do implementation. If the source is already DC, then a buck or a buck boost converter can be used depending on the input voltage level. There are many examples, two are shown here. If the source is offline AC, then flyback converters provide the variable output and the isolation that's required. There are many specialized ICs available to do the control for the power regulation and also combine the power delivery function with the appropriate feedback to the converter portion. It should be noted that when AC to DC converters go from 60 watts to 100 watts, power factor correction stages have to be added, which increase the cost and the size. Here is an example of an IC that works autonomously without a microcontroller. It supports any sink and it has dual role for power. What I want to point out is how it's possible to get the different voltages from a single winding of a flyback transformer. You can see that this USB PD controller provides numerous general purpose outputs and inputs, GPIOs, that are used to short this chain of resistors to ground at different points, thereby changing the feedback voltage that's used by the primary side controller. The resistive voltage divider is set for each of the voltages, 5, 9, 15, and 20, and the GPIO pin shorts a tap to ground to give the right feedback voltage. This works because in a flyback transformer, the output voltage is not tightly coupled with respect to the turns ratio. This is an example of a 60-watt offline AC to DC adapter using active clamp flyback technology and a synchronous rectifier. Since no power factor correction is required, it's quite compact and is 94% efficient. Würth Electronics, in a joint collaboration with ST Microelectronics, has this complete USB Type-C power delivery development kit to help users understand, extend, and emulate the whole range of possibilities of USB power delivery. It supports power delivery from source to sink for up to 100 watts and can work seamlessly with existing USB hosts. This development kit contains all the parts you need to experiment with USB Type-C power delivery. There are two sources, a 40-watt source and a 100-watt. And there's also a 100-watt sink with multiple outputs. These are both DC to DC converters that allow you to experiment with all the different types of loads and configurations. An offline adapter and cables are also included. Because the pins on the new connector are very small and close together, there's a possibility that they could short when inserted or removed. So both the source and the sink need to have short circuit protection and provide some type of current limit. When the connector is removed, power is shut off and any capacitors have to be discharged. Like any connector, the pins also need ESD protection and filtering. Here are some of the components that can be used to achieve ESD protection and EMI filtering. A TSV diode plus inductors and capacitors are used to reduce the noise on power lines. Würth Electronics has these two USB Type-C filter kits to allow testing and experimentation with filtering. They come completely populated, ready to use with both power line and data line filtering and ESD protection. With a plug at one end and a receptacle at the other end, they are merely inserted in line with the cable. The board is open, so parts can be exchanged to fine-tune the response. There's one for 60 watts and a second one for 100 watts. Though many components are necessary for proper protection, the boards illustrate how the small components do not actually use a lot of board space. Besides power, the other main purpose of USB is to transfer data. All the data is transferred using differential data lines, and therefore they also need to be protected against ESD and EMI. ESD protection is easily accomplished with TVS diode arrays, which are specifically designed for data line pairs. Current compensated chokes, also known as common mode chokes, are readily available for the data lines and have been specifically designed for USB 2.0. This is the default data speed for the standard cable. In USB 3.0 and above, there are additional data line pairs that need to be used. Each of these need their own protection and filtering, but this time designed for higher speeds. That means lower capacitance. Here again, specific TVS diode arrays combine a multitude of components into one device, not only simplifying layout and reducing component count, but increasing performance as well over individual parts due to reduced inductance. The same applies to specifically designed current compensated chokes for high-speed data pairs. Würth Electronics has put together a couple of filter design bags that contain all the components you need for filtering, for EMI and for ESD protection. They contain 10 pieces of each component needed and even some connectors. There's one kit for USB 2.0 and another kit for USB 3.0. The key message is that USB Type-C is the future of USB technology. It has been designed to be scalable, flexible, and future-proof if that's possible. It has a slim and convenient form factor that supports current design trends. It's completely compatible with all the previous protocols. Adapter cables have been defined and are usable. It's suitable for all types of devices, from phones, tablets, cameras, laptops, external drives, monitors, even power tools, and the yet-to-be-invented devices. Recall the original USB port spawned the USB flash drive, which completely replaced the floppy disk drive, and then the recordable CD and DVD drives. It should be noted that USB Type-C is not USB 3.2 or USB 4. USB Type-C is a 373-page cable and connector specification, which is a supplement to the USB 3.2 specification with its own 548 pages. These two terms are not interchangeable. Also, USB Type-C is not USB power delivery. USB power delivery is a 657-page protocol hardware specification offering up to 100 watts of power over USB Type-C cabling. Just because a product is USB Type-C does not necessarily mean it supports USB power delivery and/or USB 3.2 or USB 4. These are three individual specifications, and device manufacturers can support whichever combination they choose, including subsets within each of them. Finally, after 24 years, USB Type-C has the potential to be the first truly universal cable for both data and power for consumer electronics. There's going to be a lot of confusion initially because most charging cables are only 3 amps and they only support USB 2.0 for data. To get the higher data rates and the full potential, you have to use an EMI cable. It should be noted that the higher the data rate, the shorter the cable. Long cables will be used primarily for power. Some cables may not perform as you expect. All ports are self-protecting, so there should be no problem when using them. The cables are definitely going to be more expensive. Gone are the days of the $2 cable. Now we're going to be paying $15 to $25. But they should be more durable and the usage should be more flexible so you actually get better use out of them. The first idea is to reduce the number of cables we own, and the second is to reduce the number of adapters that we have. We should only have to carry one adapter for all our devices when traveling. The system allows for many new devices and should provide much easier interoperability between all devices across different brands. The European Union is mandating a single universal connector for cell phones to reduce the number of chargers, and it looks like USB Type-C will be it. It's an exciting time. Hopefully we can soon empty our drawers of dozens of adapters and cables with different connectors on each end, having finally settled on one. Thank you for watching. This concludes the presentation on USB Type-C, a new power paradigm.